Yes, very good morning to all. So today we are going to discuss next point from the elimination reaction. Last time we were discussed about one to elimination reaction, and it can be explained by the three mechanism: E2 mechanism, then E1 mechanism, and E1CB mechanism. And we have discussed in detail about the E2 mechanism. E2 mechanism, bond breaking and bond forming process takes place simultaneously. So first step, that is the formation of transition state, and it gives corresponding product, that is the alkene. So here there is the abstraction of proton from the beta carbon atom, and there is a removal of halogen from the alpha carbon atom, and there is a formation of pi bond, double bond between the C alpha and C beta, and you get corresponding alkene. We can use the base NaOH, KOH, sodium methoxide, sodium butoxide, in general B for base, which have ability to abstract a proton. Now today we are going to discuss about the next point. We have said that there are three type of the mechanism. We have discussed one mechanism, E2 mechanism in detail. Now let us see E1 mechanism of the one to elimination. So here again I will write E1 mechanism. In E1 mechanism, if you take the substrate like this one, here is a carbon, and here is the second carbon, 1,2 carbon atom. There is the presence of hydrogen at beta carbon and X at alpha carbon atom. The remaining valency is hydrogen atom. So here is a H, here is a H, or we can take in general. Then what happen? The reaction takes place in the presence of base. So in E1 mechanism, what happen? The bond between C alpha and X undergo complete breaking. So this bond undergo complete breaking. There is a formation of a carbocation. So here you are getting corresponding carbocation. So this carbon becomes C positive, and here is a H already. So first step, that is a slow step, RDS step. So here is a slow step, RDS step. The bond between the C alpha and X bond completely break, and further in the second step, in the first step, this base abstract proton. So what happen? This sigma bond will shift here, formation of double bond, and this H is abstracted by the base. So here there is a formation of a carbon-carbon double bond, and you can get corresponding alkene. And here is a B positive and H. So you can get corresponding alkene. So first is the substrate compound. This substrate, that is the alkyl halide. It is your carbocation intermediate. Carbon having the positive charge, that is the carbocation, and you can get corresponding alkene. So it is a two-step process. First step is the formation of carbocation, and second step is abstraction of proton by the base, and you can get corresponding alkene. So it is a E1 mechanism of 1-2 elimination reaction. So this reaction also can be explained by taking the example. So here what I will do, we have to replace the remaining valency by the R group. Suppose if I replace remaining all the valency by the hydrogen atom, or here we have to take the methyl group. For example, suppose I take here CS3, CS2. Here is a carbon, right? Here is a CH3. Here is also CH3, and the there is a presence of hydrogen at beta carbon, and there is a halogen, for example Br, at alpha carbon atom. So here is the alpha carbon, here is the beta carbon, and this one, this this carbon beta carbon, we can take also here H, hydrogen atom also, right? We can take also H, hydrogen atom. Now here you find that the reaction takes place in the presence of, for example, sodium methoxide, sodium ethoxide, C2H5OH, in the presence of ethyl alcohol as solvent, C2H5OH, or alcoholic OH. We can say alcoholic sodium methoxide. So overall transformation, this sigma bond will open here, right? And this sigma bond will shift here, and there is a formation of a corresponding product, and it gives the surge product. It gives the surge product. So here you are getting CS3, CS2, CH, formation of double bond. Here is the CH3, and also here is the CH3. So there are the three alkyl group directly attached to the doubly bonded carbon atom. So it is a trialkyl substituted alkane. So you can write also corresponding name also. Here how many carbons are there? At 1, 2, 3, 4, 5 means pentane, and at 2 there is a bromine, at 2 there is a methyl. So 2 bromo, 2 methyl pentane. So here 2 bromo, 2 methyl pentane compound, and when it undergo E1 elimination, then you are getting 2 methyl, 2 pentane. You have to write down the name of the compound when you write its structure. Always remember. So this is the above mechanism we have seen, the mechanism of the reaction in general. So it is observed that the first step is a slow step, RDS step. So the rate of reaction depends upon the concentration of the rate of reaction is directly proportional to the concentration of the substrate, because only the substrate alkyl halide, in general you can say RX alkyl halide. We can take substrate in the above case. So the rate of reaction depends upon the concentration of the substrate. So here we can remove the proportionality constant K Rx. So it is the first order reaction. Only substrate is involved into the RDS state. So the above reaction also can be explained by the mechanism also. This is the rate of the reaction. This above reaction also in the same way we can explain by the mechanism. Let us see the mechanism of the above reaction. So in mechanism, so only I have to replace the substrate. Here is the CS3. Here is the CS3. Then CS2. Here is the carbon. Here is the H. Also H. Then carbon. Here is the CH3, CH3, and Br. This is a substrate. This substrate in the first step, in the slow step, first step is the slow step, that is the RDS step. So the bond between the C alpha and Br undergo complete breaking. So the bond between the C alpha and C beta undergo complete breaking, and there is a formation of a corresponding carbocation. CH3, here is the CH2, C, H, H, and you are getting corresponding carbocation. Here is a carbocation, right? This carbocation carbocation. It reacts with the base. Base we have taken here sodium ethoxide Na plus O C2H5. It is your base. This base abstract a proton and this sigma bond will shift here. So this sigma bond will shift here and this H positive will be abstracted by the base. This will shift here and this H positive is abstracted by the base. Okay. And you are getting corresponding product, that is the CH3, CH2, CH double bond, CH3 and CH3. So I have done the same thing only with example. So this is the mechanism of the reaction. Second step is the first step, right? So in this way you have seen the mechanism of the even mechanism. So in even mechanism, we have observed that the second step is the abstraction of the proton. Second step is the abstraction of the proton. In the second step, as there is a formation of carbocation, this C positive, it also there is a possibility that there is a attack of this base O minus on the carbon atom. So when base attack on the carbon, it act as a nucleophile, and this base will act on this hydrogen, it act as a base. So when a reagent attack on the carbon, it act as a nucleophile, and when it attack on the hydrogen, it act as a base. So actually also you are also getting the substitution pattern also. You are also getting the substitution pattern. And in this case, if structure if structure permit, then also here also the O negative C2H5, it may also attack on the C positive, and you are also getting substitution pattern. Means the substitution and the elimination, it will run parallel, C2H5, right? So it is a substitution pattern, right? So here you get the substitution product. Substitution product. In this case, even though you don't write it, it also works. When you are explaining about the even here, even though if you don't write, it also works. Again, look here, there's a formation of carbocation, and if structure permit, right? If the structure permit, it may also undergo, that is the rearrangement reaction, right? So on this, as the first step is the formation of carbocation. If the structure permit, it may also undergo rearrangement to give more stable carbocation. It is called as a Wagner-Merwin rearrangement reaction, and it gives also, that is the corresponding elimination product. So in this case, even though if you write this mechanism, it also works. Okay. So you have seen the mechanism of even reaction. Then a question arises, we have to give the evidence for the mechanism. What we have said? We have said the first step is the slow step, RDS step. Second step is a abstraction of proton, and there is a formation of corresponding alkene. Right? Look here. In the previous case, in the even mechanism, what you have seen, we have said that if there is a breaking of bond between the carbon and hydrogen in the RDS step, so it obeys kinetic isotopic effect. It obeys kinetic isotopic effect. So let us see the evidence for the mechanism, right? Evidence for the mechanism. So here in evidence for the even mechanism, evidence for the even mechanism or a justification for the even mechanism. If you take the substrate like this one, in this case, what you have to do, we have to take the substrate, we have to carry out the reaction by the even mechanism, and we have to take its a kinetics, that is the rate of reaction as a kh, and we have to replace all the hydrogen by the deuterium, and again we have to take its a kinetics and we have to label it as a kd, and we have to check whether k is equal to kd or not. So here, if I take a such type of a substrate, here is a CH3, here is a carbon CH3, here is also CH3, and here if I take a Br, tertiary butyl bromide, tertiary butyl bromide. When it undergo reaction in the presence of base, for example, here is a 2 C2 C2H5OH. Okay, so it is a base, and we get the product, and of course you know that in this case the product is the corresponding alkene. So there is a CH3, then there is also CH3, there is a formation of double bond between the C alpha and C beta carbon atom. You get corresponding alkene. And for this one, we find out the rate of reaction, kinetics rate of the reaction is equal to KH, right? So here we label it as a KH, rate of reaction KH. Now in the second reaction, what you will do, we take the same substrate, but all the hydrogen we replace by the deuterium. So it is a deuterated tertiary butyl bromide. So here is a C, here is a D3 isotope of hydrogen, then here is a CD3, then also CD3, and here is a Br. So here we have taken the deuterated tertiary butyl bromide, and we take the reaction in the presence of again sodium ethoxide, then you are getting the product where there is an abstraction of a proton, that is a deuterium, from the beta carbon atom, and you are getting deuterated isobutene. Here is the isobutene. You are getting compound deuterated isobutene, and you find out the kinetics, that is the Kd, right? Experimentally, it is observed that the KH is equal to Kd. In this case, KH is equal to Kd. So experiment is observed that KH is equal to Kd. It indicates that the CH bond do not break, right, in the RDS state, right? The CH bond do not break in RDS state. RDS state. So here, if you see the mechanism of the reaction, just now we have seen previously that either you take this one or in general, this is your beta carbon atom. The C beta H bond, it break into the second step. It do not break in the first step. So the CH bond breaking is not involved in the RDS state. It is involved in the fast state. So the energy required to break this CH bond is not involved in this slow state, right? So if it break in the slow step or in the RDS step, the steady bond is a stronger bond. The steady bond is a stronger bond than the CH bond. So it requires more energy to break that bond. If it is involved in the RDS step, then they are not stable. They are not same. So here, this indicates that as the CH bond breaking is not involved in the RDS step, so here no kinetic isotopic effect. The first evidence that we can give that no kinetic isotopic effect. here is a no kinetic isotopic effect. Means the CH bond breaking is not involved in the RDS step, right? The CH bond breaking is not involved in the RDS step, right? Now, second, we have to check whether the bond between the C alpha and halogen break in the RDS step or not. So the second evidence, it is called as structural effect, right? It is called as structural effect. Structural effect. So here, what we'll do, we'll take the substrate. We'll take the substrate and we'll see whether you are having what is the effect on the reaction. For example, you know the reactivity in E1, tertiary undergo tertiary alkyl halide undergo more faster reaction as compared to secondary, as compared to primary alkyl halide. That is also in the SN1 reaction. If you take the substrate like this one, CH3, then here is the CH3, here is the CH3, and here is the suppose Br and CH3. It is your tertiary alkyl halide, and it is a tertiary alkyl halide. This tertiary alkyl halide in E1 mechanism, also in the SN1 mechanism, what happens? The bond between the C alpha and C beta undergo breaking, and there is a formation of a corresponding carbocation, right? There is a formation of corresponding carbocation. So here you are getting CH3, here is a CH3, here is a CH3 and a C positive carbocation, right? So there is a formation of carbocation. When you take the substrate like this one, CH3, CH and CH3, and here is a Br. It is your secondary alkyl halide. Secondary alkyl halide. So there is a formation of again carbocation CH3, CH and CH3. Here is a C positive. It is a tertiary carbocation. Tertiary carbocation. It is your secondary carbocation. 2-degree carbocation means secondary carbocation. And next one, if you take the CS3, CS2 and Br, primary alkyl halide. So here there is a formation of carbocation. There is a primary carbocation CS3, CS2 and positive. Here is a primary carbocation. We know that the tertiary carbocation is more stable than the secondary, than the primary. So if you see, the formation of a tertiary carbocation takes place in the E1 mechanism. So if you see, in this case, the E1 mechanism, in E1 mechanism, the tertiary alkyl halide, it use E1 mechanism, then the secondary, then the primary. Means as if you change the substrate, which use more stable carbocation, it will give more easier. That is the E1 mechanism. Same thing is observed in the SN1 mechanism. So here, after this one, we'll also take in short about the SN1 and SN2 mechanism. Why? because E1, E2 and SN1, SN2 mechanism, it runs parallel. So if you see the rate of reaction decreases as we move from 1 to 2 to 3, means tertiary alkyl halide, it gives more reaction as compared to secondary alkyl halide, as compared to primary alkyl halide. So this is the E1 mechanism in this alkyl halide. So if you change the substrate, then also the path of the reaction or rate of the reaction also get changed, right? So this is your structural effect. Means if you change the substrate, then also the rate of reaction or the path of reaction may also change. So this is your E1 mechanism and the structural effect, right? It is a structural effect. Now next evidence we can give that there is a formation of a carbocation in the E1 mechanism. So if there is a formation of carbocation, suppose there is a formation of primary carbocation. So if structure permit, it may also undergo rearrangement to give the secondary carbocation, or it may also give the tertiary carbocation. So if structure permit, it may undergo rearrangement, that is called as Wagner-Merwin rearrangement reaction. Wagner-Merwin rearrangement reaction. So it may give the Wagner-Merwin rearrangement reaction, and it further gives unexpected product as we get by the E2 or E1 mechanism. So in E2 mechanism, there is no rearrangement because bond breaking, bond forming process takes place simultaneously. So there is no scope for the E2 mechanism. There is a rearrangement in the E2 mechanism. But in E1, if the structure permit, it may also undergo rearrangement and it may give corresponding also product. Okay. So let us see how this rearrangement, it will also give a new compound in the E1 mechanism. So the next evidence for the mechanism is a rearrangement. Rearrangement. If you take the substrate like this one, here I will take the substrate. I will take the in particular example CH, then CH3. Here is a CH. Suppose if I take here Br and here is your CH3. So the name of the compound is 2-methyl 1,2-bromo 3-methyl butane, right? So it is your alkyl halide. It is your alkyl halide in general. The reaction takes place in the presence of base. Base we can write that is a tertiary sodium methoxide also, Na plus O minus C2H5. So what happened in this case? If you see the mechanism, this is your alpha carbon atom, right? This is your alpha carbon atom, this is your beta carbon atom, this is your beta carbon atom. Then there is a removal of a beta carbon atom, either beta or a beta dash, and there is the formation of corresponding product. So first step is the formation of carbocation. So this sigma bond will open on the Br. So you are getting here CH3, then CH. Here is also CH3. Here is the CH positive. Then here is the CH3. So there's a formation of carbocation. Carbocation. Then here what happened? You may get corresponding product by this way. So what happened here? This is your alpha carbon. So this hydrogen may also undergo abstraction. So this is your beta carbon atom. Suppose this is your beta carbon atom, and I can label it as a beta dash carbon atom. So you may abstract both, and what you get, you may get compound like this one, CS3, then CS3, we can abstract the beta hydrogen atom, and there's the formation of bond but the C alpha and C beta. You can get such type of alkene. Right? It is your Serge product. It is your Serge product. Serge product, right? And in this one, if you remove the beta hydrogen, then you may get the Hofmann product. So here is the CS3, here is the CH3, then CH double bond CH2. So you can get the Hofmann product. But what happened? Apart from this also, you are also getting a new product. How it is possible? Here, in the first step, we have seen that there is a formation of a carbocation, and there is a formation of carbocation. So I will write this carbocation here. Here is a CH3, right? Here is a C, here is a H, here is a CH3, then here is our CH positive, and here is your CH3. This is your carbocation form in the reaction. So what happens if structure permit, it may also undergo rearrangement in the even mechanism. So hydrogen along with electron pair, look how I write. Here, hydrogen along with electron pair, I make a circle, right? I make a circle, right? So what happens? The hydrogen along with electron pair means H negative, right? It will attack on the C positive. So this carbon becomes positive. This carbon becomes positive, and you can get corresponding new carbocation. So here you can get CS3, C, CH3, C becomes positive, and here is a CH, and there is the attack of H, right? And here is a CH3. You observe that firstly it was 1,2 secondary carbocation. It was the secondary carbocation, right? It was the secondary carbocation. I will label it as here secondary carbocation, right? But in the next one, we'll see that this carbon having the positive charge is directly attached to 1, 2, 3, 3 carbons. So it is a tertiary carbocation. Then this tertiary carbocation further it undergo elimination, right? It undergo elimination, and there is a formation of a corresponding product, right? So here this carbocation where there is a H shift takes place, H minus shift takes place. Here there is a H minus shift takes place. So H minus shift in the it undergo a rearrangement. It undergo a rearrangement. So it was a secondary carbocation. It becomes a more stable carbocation. So secondary carbocation it will convert into the tertiary carbocation. Secondary carbocation is less stable as compared to tertiary carbocation, more stable. Then further, this undergo a reaction and elimination reaction, abstraction of proton. So you are getting corresponding product. Let us see what are the product for this reaction. If I replace this carbon, this hydrogen, then you may get CH3, then CH3, right? There is a double bond CH and CH3. So this compound you can get in this reaction, and you'll find that the compound for in the previous case A, that is a Serge, right? Here is also A. There is also Serge. Both are same. Both are same. A, both are same. But if you replace the hydrogen from the methyl group, then you are also getting such type of the compound, that is the CH2 double bond, CH3, then CH2 and CH3. So you are getting also here the compound numbers. Here I can say compound A. Here you can label as a compound B, that is the Huffman product, right? And here we can label as a compound number C, that is a also Huffman product. So here you are getting the Surge product, and here is your Huffman product. In this case, it's observed that you are also getting this Huffman product, and in the previous one, the Huffman product B is there, and compound B and compound C, they are different. Compound A is the same, but compound in this case C is there. So we can say that the reaction takes place with the rearrangement reaction, and the reaction takes place with the rearrangement reaction. As the formation of C compound takes place in this case, the formation of C compound takes place only if it follow by the even mechanism. In even mechanism, there is a formation of carbocation, and if structure permit, the carbocation, less stable carbocation, it undergo rearrangement and you are getting corresponding product. So here it is a rearrangement step. The second step is a rearrangement. So it undergo rearrangement and you are getting corresponding compound. Okay, so this is the reaction, and this is one of the evidence for this mechanism. And one more evidence is there. If there is absence of a beta hydrogen atom, the presence of beta hydrogen is necessary for both E1 and E2. But suppose if there is the absence of a beta hydrogen, then whether it gives the 1-2 elimination or not, that you have to take. So here we have taken that is the E1 mechanism. Then we have written their example, and we have given also it's a mechanism. Then we have seen the evidence: no kinetic isotopic effect, structural effect, more crowding is there. Then there is a more E1 and SN1 mechanism, and here there is a rearrangement reaction. If structure permit, it also undergo rearrangement reaction, right? So one more mechanism, one more evidence you have to see. If there is the absence of a beta hydrogen atom, then how whether even mechanism is possible or not, right? So here, if you have any doubt, you may ask. Yes, if you have any doubt, you may ask. No doubt. Okay, then we'll stop here. Thanks to all, and you can leave the meeting. Thank you.
Thank you, sir.
Thank you. Thanks to all. Thank you.